from very distant events, particularly if there's lots of seismicity nearby, but the low frequency does. And in this case, for this site, you go to 10 to the minus 4, and you'll finally see some contribution from the distant events. And the way it gets into the site response analysis is that the magnitude and the distance for 10 to the minus 4, being a large magnitude at 7.1, will shape the spectrum to match that part of the uniform hazard spectrum below frequency, and that magnitude goes into the site response analysis in terms of an increased number of cycles.
Well, stick with that now and take me out to 10 to the minus 5th.
Okay.
Exceeding. I'm going to have a larger earthquake, aren't I?
At the less frequent.
I know that, but I still got to size the snubber.
Right. Well, what it's telling you is that the hazard is really dominated by the smaller magnitude events, and they're not that small. They're actually up in the.
I won't take more time. I do understand that the probabilistic dominance. I'm trying to size this snubber, and I'm trying to see how this very rare and therefore very large earthquake gets into the loading that I have to have in order to size the snubber I'm talking about.
Right.
That's what I'm trying to understand.
Sure. And it does, not great, not a large amount, but it does, and realize that it's about 1,000 kilometers away. So it gets in there finally at the 10 to the minus 4 low frequency part, but that's about it.
I'm going to have to take a class, I guess, because
it's attenuated. It's so far away.
I'm used to thinking about this in terms of if I have to design against a earthquake that's not going to be exceeded in 10 to the minus 5th, 10 to the minus 5th probability of being exceeded, I'm going to have a larger earthquake than 10 to the minus 4, and that should appear as a larger loading for this device that I'm trying to put in the plan.
Oh, it will show up. The 10 to the minus 4 will be at a higher level if you go to the next slide. The 10 to the minus 4 will be at a higher loading than, or I should say the 10 to the minus 5 is at a higher loading than the 10 to the minus 4.
Asking about is right. How do you get to that point? How do you bridge from the two things? I understand about high frequency attenuation and so on.
Okay. So if you look at this slide, you'll see that the 10 to the minus 4, the blue lines at the bottom, that's the input motions for site response at 10 to the minus 4. And then you go to a lower hazard level, higher ground motions, and that's what the green ones are. So you'll finally get the higher ground motions from that.
Okay, so it works even though I can't do the math without.
Okay. Yeah, there's some counterintuitive element to this, but if you...
It all seems intuitive. I just wanted to know if I was going from 10 to the minus 4th to 10 to the minus 5th, would I wind up putting in stronger supports? And the answer's got to be yes.
Yes.
Unless you're telling me, oh, well, but it's so rare that you don't.
No, okay. I see what you mean. Yes, the 10 to the minus 5 hazard level all across the board, the green spectra there are at a higher level than 10 to the minus 4.
And New Madrid is in both of them. It's just playing a bigger role in the blue one than it is in the green one.
That's right. That's right. In the blue dashed line is where you finally get the contribution, or a noticeable contribution from New Madrid, and particularly with regard to site response, they'll have a larger magnitude that is the input element into the site response analysis.
This is like a class. You're educating us.
Sure, yeah.
So we talked about our input for site response analysis. Our output is basically site amplification factors and soil uniform hazard response spectra at 10 minus 4 and 10 minus 5 mean annual frequencies of exceedance. Next slide. This This is a cross-section of the site that goes through the three seismic Category 1 buildings, the reactor building RBFC, control building CB, and the SWSC. It also shows different substrate material, different zones under the building, and the engineered field around each one of the buildings. It also identifies the bottom of foundation elevation for the three seismic Category 1 buildings. Note that there is a 2-to-1 vertical to horizontal exaggeration in plotting this. That's why things seem a bit exaggerated. Next slide, please. The GMRS, or ground motion response spectra, is defined for the site at elevation 224 foot, which corresponds to the deepest excavation at the site. This is the deepest foundation of the site, and it's on competent material. For foundation input response spectra or FAIRS, the elevations are defined at the bottom of foundation of each building. You have elevation 224 for RBFD, elevation 241 for CB, and 282 for FWSC. We are calculating the FAIRS to be consistent with the SSI analysis that follows, and we'll discuss that later on. This is the requirements of ISG 17. Specifically, there are two types of SSI analysis that are done for RBFD and CB. One is the partial column, partially embedded SSI analysis.
For the record, you should state what SSI is.
Oh, I'm sorry. Solid structure interaction analysis. So partially embedded SSI analysis considers only embedment in rock. And then we have fully embedded SSI analysis that considers embedment both in rock and in the soil above. And the results from those are enveloped. But we have to calculate foundation input response spectra that is consistent with each one of those. Those are calculated in this section. We also calculate performance-based surface response spectra, or PBSRS, that is calculated at finished grade elevation 290, and on top of each one of our truncated soil columns that are used for partial column analysis. Next slide, please.
On that slide, I was looking at this slide. Go back to that slide, please, the figure.
With the figure.
Yeah. What are those vertical blue lines?
Those are the boreholes that happen to be in this cross section.
Okay, understand. Thank you. And you drilled those, I mean.
Right. So, next slide, please. The site amplification calculations are following requirements of NUREC BR 6728, we follow approach 2A, Reg Guide 1.28, and ISG 17. Basically what we are doing is that we are taking the high frequency and low frequency inputs that Jim talked about at hard top, at 10-4 and 10-5 mean annual frequencies of exceedances, and propagate them through the soil columns that we assign for each building. We use three base soil columns for the analysis based on the footprint of each one of the buildings. So we have an RBFC soil column, we have a CB soil column, and we have an SWSC soil column. And then as a conservative measure, we envelope all the results coming out of RBFC and CB soil columns. So the GMRS is calculated as the envelope of those two. The RBFC and CB FAIRS and SSI are calculated as the envelope of those two. For FWSC, because it has a small footprint, we just use the soil column corresponding to that. Next slide, please. This is an example for RBFC soil column, the site amplifications at the GMRS horizon. On the left-hand side, you have the 10-4 amplifications. On the right-hand side, you have the 10-5. The high frequency and low frequency amplifications are shown high frequency with dashed lines, low frequency with solid lines. And as you can see, they're pretty much the same. For 10-4, 10-5, high frequency, low frequency, we're getting the same amplifications. The reason is that the material below the GMRS elevation is basically linear. So we are not getting any difference in amplification. It's not dependent to our input. We have similar results for all other elevations of interest and other inputs in the FSAR in section 254.
So do these include the damping factors?
Yes.
5%?
Well, no. The dampings are coming also from the site investigation. So we have a damping for the soil column, for the soil properties that are included in the site response.
Okay. Because it's a time history.
This is the site site amplifications are calculated using RBT, and they include the damping. The amplifications are calculated as the ratio of the 5% response spectra at the horizon of interest to the bedrock.
Thank you.
Next slide. This is an example of the actual acceleration response spectra, again for the GMRS horizon, using the RBFC for column at 10-4 on the left and 10-5 on the right. In both these figures, the green curves are inputs, the blue curves are the outputs. The high frequency is shown with the dashed line, low frequency is shown with the solid line. Notice that there is a very different scale in the vertical axis. There on the left-hand side, the peak corresponds to about 0.8 G for 10-4. On the right-hand side, the peak corresponds to about 2.5 G for 10-5. So there is a big difference between 10-5 and 10-4. The uniform hazard response spectra is calculated as the envelope of the low frequency and high frequency results for each case. And again, we have similar results for all other soil columns and horizons of interest presented in there. Next slide, please. So in this 2525 so far, what I've talked about is site amplification factors, uniform hazard response spectra 10-4, 10-5 that are used for GMRS horizon and FAIRS horizons consistent with the SSI analysis. These uniform hazard response spectra are used in section 2526, which is my next topic, in calculation of the actual FAIRS and GMRS as a design response spectra. If there are no other questions, I can just roll on to the next one. So in section 2526, we calculate the performance-based design and response spectra, or DRS, and these are basically our GMRS, horizontal and vertical, and FAIRS and TBSRS, again, horizontal and vertical. Next slide, please. These design response spectra are calculated following performance-based requirements of record 1.08. The horizontal GMRS, FAIRS, and TBSRS are calculated from 10-4 and 10-5 uniform hazard response spectra using an appropriate frequency-dependent design factor that is coming out of record 1.08. As I mentioned before, we envelope the results coming out of RBSD and CD soil column to come up with GMRS, RBSD, FAIRS, and CD FAIRS. For vertical direction, we use an appropriate V over H ratio that is determined using NUREC 6728 procedure. And we apply that to the horizontal FAIRS and GMRS, etc., to come up with the vertical direction. Next slide. The GMRS horizontal and vertical is shown in this figure. The dashed blue line is the horizontal direction. The solid red line is the vertical direction. Again, similar plots for all other FAIRS and TBSRS parameters in there. Next slide. In this slide, the FAIRS for RB, FD, and CD are shown and are compared to the CSDRS, ESDWR. On the left-hand side, you see the comparison for horizontal FAIRS. On the right-hand side, you see the comparison with the vertical FAIRS. The red lines correspond to RBFB. They're lower because it has a lower foundation elevation, and then the blue lines are the foundation response vector for control building. The dashed lines are corresponding to the partial embedded analysis, and the solid lines correspond to the fully embedded analysis. In both cases, you see that there is an exceedance in mid and high frequency ranges from the CSPRS, and this exceedance is the basis for having NAPS departure 37-. Next slide, please. Similar information are shown for FWSC. On the left-hand side, you have the horizontal, right-hand side, you have the vertical, and again, you have that mid-frequency range exceedance when compared to the CSPRS. Next slide, please.
For the record, FWSC is Firewater
Service Complex. So in this section, we talked about calculation of GMRS and TBSRS, FAIRS for each building consistent with SSI analysis, and we showed that GMRS and FAIRS exceed in some frequencies the CSDRS for ESDWR, and this is the basis for NAPS departure 37-1. Because of this departure, we do site-specific seismic analysis of all seismic category 1 structures, as will be discussed later in 2001 and 2002. So any questions that you have?
So Jim, you're ready for your Thank you. I might want to grab them out. Okay, that's all right with
This is Jim Shea again from the NRL staff, and we have the panel number 2 presenters, Alice Stevie, Vlad Grazier, and Weijing Wang, and we'll start right off with this is you.
Yes.
Alice. Yes, Alice, take it away.
So at one point, I might want to grab them out. Okay, I'll let you.
Yeah, go ahead.
Okay. So my name is Alice Stevie. I'm a geologist in NRO, and I was the lead reviewer for the geology sections 251 and 253. My review covered only new information since the 2005 ESP FDR. So this includes the geologic aspects of the Mineral Virginia earthquake and the additional borings done for the COL. Because of the Mineral Virginia earthquake, the applicant implemented a geologic field reconnaissance program to look for surface deformation associated with that earthquake. Because the applicant did not docket this field reconnaissance report, I asked several REIs to bring that information onto the docket so I could make my safety findings. In addition, many other geologists in other institutions like USGS and various academics were also looking in the landscape for surface deformation. So I reviewed additional pertinent publications there. And my site audit included visiting several of the field sites that were included in the applicant's field reconnaissance. I also reviewed original source materials regarding the discovery of the Fall Bay at Northampton in 1968. And I'll talk with you in a slide or two, because this was apparently a public comment in a previous ACRS meeting. So they asked me to say something about that. So next slide, please. This view is a map in cross sections of the aftershock sequence for the Mineral Virginia earthquake, and this defines a slab, a southeast descending slab in the cross section over here that was subsequently named the Quail Fault by USGS. And this is where that slab is when it's projected to the surface on a map section, and it projects to the surface right about here, and this is the uncertainty around where that projection is. This helped define for the applicant where they were going to do their field reconnaissance to locate surface deformation or of liquefaction or any other deformation feature. Next slide. This is the scope of the field reconnaissance report, and this is, they collected, the applicant collected LiDAR, and this is LiDAR data can be used to get very high resolution topographic information to determine if there's any young fault scarps or something, or elevate or deformed river terraces or things like that. So this is the extent of their LiDAR. This is where the Quail Fault earthquakes project to the surface. This is where the surface fault is, or that fault projects to the surface. It doesn't come to the surface.
What do you mean, Alice? LiDAR means? LiDAR is?
Light detection and ranging, and it's a laser pulse from an airplane that crisscross, and it's a remote sensing sort of thing, and they collect the different range for the returning signal, and they can determine very precisely, very close, the topography, and they can strip away buildings, they can strip away tree canopy and things like that, so they can get a very high resolution look at topography.
Thank you.
Because this area, this landscape is, typical Virginia Piedmont landscape is covered with all kinds of forests and things like that. So it's hard to do field reconnaissance and find something that would be a small feature, which is what you would expect from that size earthquake, if anything. So that's the extent of the LiDAR. This is where the earthquakes were, and you can, in these dark lines are where they did their road traverses and checked outcrops or geologic contacts, and then they also had continuity all the way back to the site, which is over here, because they wanted to see if there was any connection, perhaps, with any of the faults, the older geologic faults that they knew in the area might project back to the site next. And in addition, still using the LiDAR data, they pulled off the elevation.
Can I ask one just understanding? I'm not a seismology person. You said the quake never came to the surface. And
that's okay. Yeah.
You don't need another slide. Well, do whatever you want. But
one more. There. Okay.
So all this mapping is just a surface topography of the land, right? I mean, if nothing came to the surface, you're just mapping what the land surface looks like. Minus trees, buildings.
The Quail Fault is defined only by aftershock sequence. It's not defined by any surface geology. However, on the surface, there are many faults, and many of those faults are very ancient. And there was speculation because that was a northeast trending seismic aftershock kind of fault. So it matched a lot of the other geologically known faults in the area, and it's close to the surface. The aftershock sequence is close to the surface, so we were speculating that maybe there was some evidence of surface deformation, and that could have been where the fault could have projected to the surface. You see, there's no aftershock here, right? That's just a modeling to project to the surface. You want to do that?
No. I'm a seismologist. I just wanted to add a little bit to what Alice just said. These dots are aftershocks. There is
locations of aftershocks?
Yes, okay. and there is a notion in seismology that the aftershock sequence of the first few days or maybe a week counter the full fault zone of the main shock. This is why kind of the search for surface trace was on the continuation of this, on the projection of this on the surface. Sorry, I didn't want to distract. No, I just wanted, basically this notion of aftershocks countering fault zone. But aftershocks of the first maybe a week, not more. After that, they have a tendency to spread out and showing bigger zone.
But you think the initial for the first few days or a week, whatever it is, they these things bound the general underlying fault that was below ground? Is that what you're
Correct.
Okay, all right. How do you define these points on the cross-section where the aftershock occurred?
Okay, these points are coming from seismic investigations. What is going on? Basically, there are stations around, and
fucking bang it! Fucking see what you're doing! That's what fucking damn it.
What's the matter? Who's at the door?
Fucking turning the wheel.
The bartender from the floating red.
Okay?
He was looking for your dog.
I know what you're doing all the time. I know you ain't doing anything wrong. Okay? You understand that, lady? You don't know what you're doing.
Whether you're new to Medicare or not,
we have to know what you're doing all the time.
About 80%
all right?
of your Part B medical expenses. It's up to you to pay the difference. So think about an
fucking
AARP Medicare Supplement Insurance Plan, insured by United Healthcare Insurance Company. Like all standardized Medicare Supplement insurance plans, they help cover some of what Medicare doesn't pay.
God damn it.
I did a little research. With a Medicare Supplement plan, you'll be able to stay with your doctor.
Oh, you know, I love that guy. These types of plans let you visit any doctor or hospital.
Quick, if you're going to get the data for the aftershocks in the first week, right?
that's very true. That's very true, and this was, as far as I know from the meetings and I attended, it was a big effort from United States Geological Survey, from Virginia Tech University. I probably forgot somebody, but it's a big group of people, and they published a lot of papers, and actually another set will be presented next week at the Eastern session of Seismological Society. But basically, it's a joint effort of many organizations to get these precise locations of aftershocks.
Thank you.
Sorry.
No, it's okay. So,
No, I got it. It's a quick mobilization of seismological instrumentation to get out place in place and then see what you get.
Exactly, and also just to add to this, since it's my whole life, some organizations, they keep a lot of spare instruments specifically for this task, for recording aftershocks and tracing well the main shock using this. And they have a group of people who is supposed to be ready to go immediately.
So they were happy campers then. They were probably having a good time.
Sometimes
I would have been.
Sometimes it's true, sometimes not.
Well, that said his whole life, but he's only 22, so don't.
Yeah, I wish.
Okay, so the geologists went out to look for surface deformation in that area where the epicentral location is. So, in addition, they looked at river profiles. This slide is showing in the various colors the different streams that cross the epicentral area, wherein they pulled off longitudinal river profiles. River profiles are usually nicely graded, and they smoothly descend down to the mouth of a river or a creek. But if there's any kind of deformation that's expressed at the surface, either as a sharp, like a fault scarp, or even as kind of like a warp zone, an arch, it may show up in the longitudinal streams. And they also examined the river terraces on South Anna River.
Longitudinal stream,
longitudinal
water
stream
running along the ground.
Going from the high elevation down to the lower elevation in that area, and they used the LiDAR information to get the very high resolution kind of, so they could see small offsets or small nick points or things like that. So you can see that the profiles cross the epicentral area, so that was a good place to be evaluating those streams. There's no obvious signs of deformation. There were some nick zones and some rough places on the profiles, but they are attributed to changes in lithology and locations where other watersheds were entering in the stream, so the stream power goes up, and that may cause some changes in that smooth longitudinal line. To the next slide. So in addition to what the applicant did, USGS, notably Burton et al., went out and did some geologic mapping. So in this area, there are several generations of geologic map, and they are conducted for different objectives, and they're done at different scale, and it's a patchwork of coverage. And this particular map was done specifically after the Mineral Virginia earthquake happened. They went out there afterwards, and they mapped it at a scale of 1 to 24,000, which is a very fine, a high-resolution kind of mapping for geology. And they found 2 additional faults that were not previously known. And they looked in the area. So in this area, this is where all the earthquakes are at depth. And over in this area where the projection of the Quail Fault would have been, they discovered two additional faults. They're not new. They're old faults. So they are not, and they are not known to be active. They did trenching, they did test pits, and there was no quaternary disturbance in the soil. So those are just old faults. They're just additional.
Old faults, but newly discovered.
Newly discovered. Old faults, but newly discovered. And these are the faults that we kind of like considered because they showed up in the literature right after the Mineral Virginia earthquake as being maybe actors in the Mineral Virginia earthquake. And Burton et al. Went out and looked at where these things are. They relocated some, like the Chapawamsik was relocated a little bit. It is situated to the west of the epicentral area, so it is structurally below the aftershock sequence, so it is not associated with the Mineral Virginia quake. Going down here to the Long Branch, this one is to the east, and it is structurally higher than the aftershock sequence, so it cannot be an actor. And the 2 here, the Harris Creek and the Roundabout Farm faults, those are the ones that are newly identified by Burton et al. And they did trenching, but no quaternary, there's a misspelled word there, there's no quaternary deformation for those faults. Fault A, I asked them, I went back to the original material, as best I could get it, from the 1968 through 73, to examine how they investigated fault A, NIS and RAI. So there's no alignment of aftershock data with that fault. And the field reconnaissance and LIDAR data that the applicant did from the site all the way out to the epicentral area, there was like that continuity coverage that they did not find any reactivation or surface deformation. And when I went and did my field audit, and we went to visit several of these waypoints, there was nothing to be seen. And then, of course, the previous ESP SER done in 2005 said that the fault was, would you give me another slide, was certainly older than a million years old. So this is, I'm sorry, it's a little fuzzy. It just didn't import into the PowerPoint slide. This is the site. This magenta line is fault A. Down through here. This is Unit 1, Unit 2, abandoned Unit 3 and 4, and this will, if you can see that's going to be where the new Unit 3 is. So in 1968, they found it in the excavations, right here. And then subsequently, Dames and Moore did a trench here, they did a trench here, and then they did a trench here. And they determined that the fault was very old. So they did potassium argon dates, and they got ages like 239 million years old from chlorite seams that are within the fault zone itself. And they got 214 million years old for the fault gouge that was also in the fault zone. But of course, stuff that's in the fault zone, it's not a single plane, it's a zone. It's a bunch of shears and some ductile deformation, some brittle deformation. It was originated as a thrust fault, and it was reactivated later as a normal fault where there were brittle features, but they had a soil